details. That's all right. Shall I repeat everything?
Yes.
Yes, so the question is, when I add loss functions, do they have the same units? Good question. Usually we do some work before to put everything in unitless parameters. There's ways to scale them to be in the same thing. Yeah. Okay, move on. All right, so now we need to define initial boundary conditions. So what we call initial condition is the value of my dependent variable at times equal to 0, and I need to know it. Otherwise, these differential equations will not have unique solutions. And then if we talk about space, we call it boundary conditions, and there's two types of boundary conditions. One is called division boundary condition, when you define the fields as particular values of x, or Neumann boundary conditions when we define the derivatives. They are a mix of the two, but for now, let's just keep it simple, okay? All right, now let's do the neural network addition. How do we solve differential equations in a neural network way? That is not very difficult. You have the x, go through my neural network, I get my UN, and now I write down my differential equation as I wrote it before. Now I'm gonna put the f on the other side. Before I do that, let's ask one question. If it's not on the chat or here, how do I find the derivative of u? Yeah.
The derivative.
Yeah. Put you on the spot, someone.
Say what?
I put you on the spot. Anyone? Back propagation, yes. So I can do it analytically, automatic differentiation, back propagation. We'll do it analytically. So those derivatives are not numerical. They are exact, right? Given the parameterization. Okay, so I have that. I know this in most cases. I know this. I'm ready to rock and roll. So if I put the f on the other side, I'm gonna call this the residual. That's the how well we satisfy differential equation. And then I have, of course, the initial condition, boundary conditions, which is the difference between what the neural network tells me at t is equal to 0 and the correct answer. This is, I know that, right? Okay, so this is called the residual. So my loss function now is the sum of the squares of those things, subject to scale, okay? And in this case, the scales are fine, I don't have to. Caveat, side remark, there's another way to satisfy differential equations, which I'm not showing. Let me finish this. There's another way to satisfy the boundary condition, initial conditions without having to put this term, which is by reparameterizing everything. I'm not showing it here, but if you want to go on the board and explain. Yes.
So first of all, there is a comment saying that please repeat the questions from the room.
Yeah.
And my question is, so do you not have to worry about weighting the RD and the RD when you compare to the loss function? I mean, the boundary.
Yeah. So the question is similar to what we were saying before. The question is, are there any weighting factors here? The same I said before, if we put them in the same scale, no, I don't have to worry about it. And second, as I also said, in most cases we don't worry about that. We only have that, so we don't have to worry about that. So it says, no, I can do it on the board.
Yeah, I mean, my worry is that RD is going to be comprised of a large number of elements.
Yeah.
It's going to be a much larger array than RD usually.
You minimize both. If they both go to 0, I'm happy, right? Not so important.
Yeah, but the RD square term might overwhelm the RD square. Usually what happens when we try to do SAD first.
What's CP?
Spectral energy distribution.
Yeah, I mean, if you put, okay, first of all, let me show you how to get rid of the B so you don't worry. So if I do this.
Can you move your laptop a bit so people can see the?
Do they see now? I can't see what.
I think so.
If t is 0, this goes away and I have u naught. Okay. So there's a whole industry of how to reparameterize so the boundary conditions can be satisfied automatically. So I don't have to worry about that. Okay. But in general, if we put them in the same scale, then it's not a problem. We can divide by U naught and everything is in the nice in the scale. Now, one thing that I want to mention here, so you maybe worry less, is the fact that when you fit data, there is something called the irreducible error. There is no irreducible error here. So in principle, and since neural networks are universal approximators, you can put this loss to machine precision. And we have done it for simple fraud. 10 to the minus 19, 10 to the minus 20. So they both went down. Okay. All right. So with that, I said if we have data, we can also include them. So again, maybe there's some scaling factor there, but just I can throw everything together. Okay. But the most of the talk I'm going to be talking about is without data, just satisfy this differential equation. Okay. So we have that. Now what we do? Nothing. We just minimize the loss with respect to the parameters and hope for the best. So again, neural networks are universal approximators. In principle, if I increase the number of nodes and I keep increasing it, I should be going down to 0, right? Now, one question you may have is, well, I put some x, I get some un. What domain do I satisfy the differential equation? Right. So this loss that I do is going to be the sum over all the examples I have. So what domain do I satisfy? Well, it will depend on how I sample x, right? So I try different x's and I see what they use, and I want it to satisfy in every possible x that I do. But in principle, the domain of x could be infinite, right? So if the domain of x is infinite, this is untractable, so we're stuck. So we choose the domain of x, but once we choose the domain of x, there's a question, how do we sample from x? So there's a couple of ways of doing it. We can use regular intervals or randomly. So you put the domain, the range, and you randomly choose x's from this. Randomly usually works the best. We have tried 1 gazillion different things. We try adversarial networks, we try reinforcement learning, we try all kind of reinforcement learning. Ask him later if you want. It seems that randomly is tough to beat. But there's ways to do this better. Sometimes you want to sample in logarithmic scale, especially if you believe that your solution is much more important at the small x's. Sometimes we even sample from Chebyshev polynomials. So if you want to get the edges more important. Different ways of sample will give you slightly different result, not different result, but you'll converge faster to the solution. Okay. All right. So that's it. That's all formulation I have. That's all you need to know. Now you can go and do it, solve your differential equations and things. So we have tried this with various degrees of complexity of differential equations. As you can see, we start with ODEs, then we went to PDEs, first order, second order, linear, non-linear, etc., etc. We have tested it in multiple ways. In this work, we have not gone into stiff regime, though now we're doing stiff regime, which is yet another talk, how to go into the stiff regime. But for non-stiff regime, we have tested it extensively, not only us, but many people, and then you can see it just does remarkably well. This is for a couple oscillator. This is dumb nonlinear oscillator, which is not linear. And you can see the solutions look exactly like the exact solutions here. Okay. All right. So now at this point, you say, how I'm going to use it? Yes.
Do you have any sort of regularization that avoids higher order oscillations and constraints like the higher derivatives beyond the ODE that you're actually specifying? Is there an implicit regularization?
That's a very good question. I'm going to repeat it and rephrase it a little bit. The question is, what do we do here? We satisfy the differential equation. What if we take the derivative of the differential equation? Can I put it as a regularization? Is that?
Yeah.
The answer is yes. It does work better, but once you put more derivatives in, this automatic differentiation, as is implemented, makes things slower. So we haven't seen great advance to do that, even though it converges in less epochs, but the number now that every epoch takes longer, right? Yeah. Yes.
So have you tried this with the chaos generating equations?
With the what?
Chaos, when you expand chaos.
Yes, that's what I mean, stiff regime in some ways. That's when you're mixing scales, right?
Mixing scales, but when small deviations can, I mean, when you have branching.
Yeah, it's in the same family of things. This I call it stiffness and chaotic system. Have we tried? We just start doing it. I mean, we have tried with some minimal success in some cases. But if you go to really chaotic or stiffness regime like the sun or a black hole, forget it.
Or
Okay?
the multiple,
Yes, that's another talk. We have the one that is that works actually. It's fantastic. Yes. But it's not a straight, it's not like this. We have to do some, we have to take care of some stuff. Yes.
On the samplings that you mentioned, like the ideal strategies would be random, but in these toy problems, we sample infinitely, we cannot sample infinitely in our real set of data. Do you see notable biases or difficulties in training when you have realistic sampling strategies like what astronomers have, for example, pseudo-periodic strategies due to solar and lunar cycles?
I haven't tried that. Maybe
Yeah,
we should
okay.
try it. Yeah. Yeah, we haven't tried these pseudo periodic things, yes.
So when you try this for the harmonic oscillator, so what do you observe now? Because it has, so it does this, let's say the energy is conserved, or do you observe something?
Yeah, yes.
Repeat the question.
Yes, the question is, if we try this with harmonic oscillator, will the energy be conserved? Yes.
But you are not exactly,
Yeah, but it's 10 to the minus 6, right?
okay. And so also you must be observing some loss in this, the predictive accuracy.
As I go further in time.
No, yeah, so it's just a period.
No.
Because
So, sorry, so you lose your predictive power where?
I'm saying that, so first, I guess what you're trying to do is predict the displacement as a function of time.
Mhm.
And I think the graph showed that when you're solely trying to do that, it is not really following the conservative method.
Yeah.
And now here you're trying to minimize both of them together.
Yes.
So it should be compromising on both the ends, right? So what am I saying is, does that displacement predictive power, does that go down? So
Yes, yeah, I mean, I have another example I can show you, which is not energy, but parity, right? So if I do data, the parity is not preserved because there's a few points there, a few points here that they do it, right? If I only put this, I have perfect parity. And if I put data and everything goes in between, right? Yeah. So the data will push you away from satisfying the symmetries. These will push you towards satisfy the symmetries and not satisfy some of the overfitting you do, I guess, in that case. Minimum limited sample. Yes.
But one more thing I was asking is, when you, so if you like training on larger and larger samples, so for example, you're just trying to predict the displacement as a function of time.
Yeah.
And you are like training it vigorously.
Mhm.
So does it show improvement on the other, on the
Yeah.
conservation of it?
Yeah, if the data are not biased and if the data are from a harmonic oscillator,
So
eventually you're gonna end up with a reducible error that you cannot do anything
without even penalizing the differential.
without, yes. Yeah.
So what am I?
So you're saying if I have an infinite sample and I do a regression, will I get the right underlying dynamics? Yes. If the data are true, except that you still have the reducible error there, right?
So you are introducing this differential equation loss just to correct for some bias in some.
Yeah, exactly. Right. Yeah, yeah.
That's what's good.
Yeah.
Why did you do that?
We'll get to that.
I mean, why did you do this approach at all?
We'll get to that.
Okay.
I have 6 slides for you. Okay. Yeah.
Which activation functions are you using? Because I've seen in previous work that.
Active
The next one.
activation function is a hyperparameter depending on the problem you do. If you do ReLU, for example, and you have second order differential equation, you're gonna run into trouble because ReLU doesn't have second derivative, everything goes zero. So we choose not ReLU or we turn everything to first order differential equations, that's fine. If you are having a problem that is kind of periodic or semi-periodic, ReLU and all these things are very local activation functions. So what you can use trigonometrical activation function, which gives you a little bit of the extension. However, for the hardcore machine learning neural network people, they get a feed, they go on the ground and they get foam out of the mouth when I said I use sign, because sign will introduce a gazillion little local minima, right? So it's kind of anathema to use sign because it creates this little local minima. But for some of the problems, we see tremendous improvement by using some trigonometrical function. Okay, let's move on.
One question from the
Yeah.
chat from Mangyang.
Yeah.
It's like, how fast is the NN solution?
How what?
How fast is the solution compared to RK4 and finite alpha?
I'll get to this thing. These questions, I'm going to be addressing it, all of them together. So, okay, so here's what I said. You go and do that and you write your own PyTorch or anything. Or if you choose, we have a library called NeuroDiffEq. It's fully documented, optimized, and the likes. Is pip install NeuroDiffEq. Look at the documentation. We have examples. It has all kind of things you can do. All right. Now, the question, why? You ask. Okay, here's your answer. All right. So traditional methods for some differentiators have lengthy history. Every time I give the talk, there is an angry person on the audience and this 150 years of numerical methods, why we do that. Okay. So why do we try to do that? Let's compare, right? So see the pros and the cons. It's not only cons, right? So why using pin? So I have put it into two things. First one is differential. My solution is differentiable. And why is that important? Well, because I can do a lot of fun things with that. I can discover parameters. So I can find actually potentials. We have done many examples of that. Finite difference are not always differentiable. There is some degree of differentiability you can do, but you have to know what you're doing, and there's a degree of that. So second, it's fast to evaluate. Once I train the network, and I spend a week training it, then it's fast because it's just a forward mode, right? Now, why is that important? Think about statistical inference, not the inference machine learning piece. You do an FCMC, you have to do evaluations all the time. So on some cosmology paper that we have seen an increase of order of 40 by doing this. We train it, and then we doing inference on the parameters, and because now it's fast, I can just do it very fast. Alternatively, with finite difference methods, you have to integrate them. You change the parameters, you integrate. You change the parameter, you integrate. So that's number two. Number three, which I strongly believe in, most people think that's not important. If you have finite elements, finite difference solution in a multi-dimensional space, and I ask you to give me the solution, you're going to send me terabytes of data, right? So, because it has to be on the mesh. When I give you this solution, what do I give you? The weights of the neural network. So I can exchange it. And more importantly, which is not on the slides, this is going to be PyTorch or TensorFlow. And if I ask how many of you know PyTorch or TensorFlow here, raise your hand. It seems that everyone. If I give you a solution from Oak Ridge on the things, and I have got this, is some proprietary thing, the solution that I have to learn how to use, and it's usually some C++. So that it makes it easier to share solutions. Number four is parameterizable. So the parameters can be input to the neural network. That's not in this talk, it's another talk, how to do that. So these no parameterizable here. Maybe you argue there is some in the finite elements, numerical continuation method, that you can do that, but you can only do it in small steps and only if you believe there's some quadratic or linear dependency. Here you discover the whole thing. Okay, we don't overfit. There's no overfitting in both cases. That's not too much. Yes.
I know you said parameterizable is not in this talk, but can I ask you how do you envision using that?
At the end of the talk, I have a surprise for you. There's a whole series of talks coming to you in January. I'm giving a whole course.
We can do a whole course here.
Yes.
Please.
I'm getting your appetite. So Compute Fest January 8th, we're giving a full course. Is 10 lectures with exercise quizzes and the whole thing.
I'll have Samuel take it.
Yeah, yes, you.
So
You should take it too.
you say you don't overfit. but we were also very careful about noting where we have support.
Yeah.
So do you consider out of your initial training set, do you have any confidence in?
Okay, I think I know your question,
Okay,
and
yeah.
as a great professor, I anticipated, so I have a slide in two slides.
Okay.
Just hold on, we'll get there. Okay, now, okay, so I'm a good salesman. I sell this, but let's talk about the bad things, right? So the first one is slow to train. Anybody who train neural networks, these big neural networks, there are some problems take us 3, 4, 5 days to train. Finite differences don't take so long. I said finite difference for all numerical other methods. So here is a hard to satisfy boundary conditions on irregular symmetries. You remember I said there's a whole industry to do this parameterization to satisfy, or we put an extra term, and then there is issues of scaling. If you have boundary conditions that are convex and nicely defined, is not a problem. Once you get away from that, it's a nightmare. Okay, so where if you have a problem like that, I don't think, I mean, it's doable, but it's not elegant and it's not nice. Where with finite volume, finite elements, etc., you just start there and there's no problem, right? You just put your grid there. And hard to tune. Someone asked, what is your activation functions? How many neurons you put? What's your learning rate? What is your optimizer? All these things, you have to do them sort of by hand, right? And it takes effort and time. Okay. So, and finally, which is the talk today, which bothered me a lot, is that when you do finite difference or finite elements or any one of these, you know your error bounds, you know how good your solutions to some error bound. So if you, let's say you calculate orbits of satellites that you're going to send in space, and you do with the traditional method, there is an error bound. I know how well my calculation is, right? Up to point, right? I mean, I can do error bound. It's going to be there. It's going to go 100, I don't know, 100,000 miles from Earth, or the worst scenario is 90,000. When I do it with that, I'm going to tell you it's 100,000 miles for Earth, but it may hit us too. So that's for important problems without error bounds. I think this is very limited. Okay. And the big challenges, see? So back to this, the 3 big ones, I added the next one. Computational complexity takes forever, error bounds, and generalization outside the training domain. I think that's what you're asking, right? I have no idea. No, I do have a lot of ideas, but I don't think it's a solved problem. We have tried 1 gazillion things and kind of works, but not in an elegant and nice way. So it's kind of hacks, but I'm sure it's gonna happen. Someone else. So the rest of the talk is about error bounds again. Okay. All right, let's talk about error bounds. What do we mean by error bounds? I have a bunch of things to address. We have a paper out. This is summarized some of them. The mathematics get a little bit complex, so I only emphasize on 2, 3 things. Well, actually, 1 thing very well. The rest you're gonna have to go and read it yourself. So what are error bounds and why we care? Well, error bound is a measure of uncertainty or possible error in numerical calculation. And is in this particular, what I want is the upper limit. I don't really concern about posterior, predictive posteriors and all these things. I'm in the wrong group to talk about that. But another talk for another time, we have used error bounds to do full predictive posterior. If you invite me with Chinese next time, I'll do that. Okay, but what I want to know is the upper limit, right? And I think that's important. I think we don't have it in the slides, but I'm gonna, because I'm only focusing with no data for now, right? If I satisfy the differential equation, there's no data, there's no stochastic error. So it's only epistemic error and only misclassification error. So, but in principle, since neural networks, and I said many times, the universal approximator, I should be able to turn the loss to 0. So you may ask, well, if your loss is small for some unit you put, why do you care finding the error? Okay, so this is a fundamental thing I want to explain. One is how well I satisfy the differential equation in some regime, and the other is how well is my solution compared to the true solution. Why they're different? Because think about Earth, asteroid going by, okay? I satisfy the differential equations perfectly, and I make a little mistake here, okay? Just for one little delta t. I don't satisfy the differential equations for that little delta t, right? And then I continue, satisfy the equations perfect, okay? Now, if you look at the overall loss I have, it's very small, right? 10 to the minus 7. But if I go like that, and I make a little up, and I end up there, but the true solution end up here, right? So that means the correspondence between the loss, the overall loss, the empirical loss, and the error in your field, in your solution is not exact. So that's what we embarked into that, right? So we've seen it, and at the beginning, I was convinced that, hey, I don't need to worry about it. If the loss is zero, it's zero, but the loss is never gonna be zero. And you can see another example. Let's say this is a true solution. So you get this. Yeah. You good?
I'm so sorry, could I interrupt with a question here?
Yeah, of course.
So I'm maybe you covered this basic idea a little bit earlier on, but suppose your numerical solution didn't look this nice, but stayed within that band, but had a lot of oscillations in it, or had some other systematic trend over this interval. That wouldn't be so great a solution. So it is this simple idea of sort of the mean RMS difference as the residual, is that something that's really baked into this whole procedure?
I think it is exactly that. I mean, what you say is a little bit more subtle, as the overall loss is small, but your solution is not good, right?
Yes, in some sense, in some other sense.
Some sense, yes. So, yeah, I think your example is a little more subtle. The example I'm doing on the board is a little bit pronounced, but it falls under the same category. Your loss can be small, but your solution may not be good enough. Okay, is that okay?
Yeah, and especially in nonlinear systems, I would think this would be
even more
come up all the time.
Yeah, I agree. Yeah. All right, let me give you the obvious example, and then we get into the other one. Right? So let's say I satisfy the equation exactly, and then I make a little, for some reason, a little mistake here, and then I satisfy. Now you see that if you look at the loss here, it's going to be like that. And if I sum it up, the total loss is small. But here I'm making huge mistake. That's the difference between the asteroid hitting us or not.
Don't you have a prediction loss?
No, I don't know the true solution.
When you fit the data, right?
I don't have data right now. I'm just looking at epistemic error. Okay, just looking at the epistemic error. And if I put the data, yes, the MSE will increase. But let's assume we have very little data or no data. I'm making a prediction further down, right? So if I knew the correct solution, I will be golden, but I don't. So here we have the U to be the numerical solution and V to be the exact solution. So the error bound will give us the guarantee that the difference between them is smaller than some bound. Okay, that's what I'm after.
For all t.
Sorry.
For all t, or some average over t.
Some domain. Everything I do in a domain of t. Yeah. Okay. And I had it. All right. So there, as I said, a good professor, so very good. Anticipate the question. All right. So as I said, this is kind of why do we care about that? Boosting confidence in numerical results and ensure reliability, guiding decision making, especially when we make decisions. We need to know that error bound, what is the worst case scenario or best case scenario, and then for allocating the resources and adding. So this number 3 is a little bit more involved. because what we start doing it now, instead of training until we run out of credits or something, or the loss, we say train it until my error bound is satisfied. You just give a tolerance and you can do it this way. And then we can use it to choose between models. Okay, now traditional methods like finite difference in elements, as I said before, they have a very good framework to do that. As I said, 100 and so many years of research, and they use this thing called the truncation error. Now, pins lack this. They don't have. Pins stands for physics for neural network, what I'm talking about, right? So when we start doing that, it came because I submitted a paper, the referee said, I don't believe anything you said there. How do I validate, right? I said, the referee is right. Let's think about it. So then there were a couple of papers that are out trying to do error bounds, but the way they do it, they're trying to put the complexity, trying to find the bound based on the complexity of the neural network, right? That was kind of the line of research I've seen. They will have two problems. One is I never understood their math because they're very mathy and they use notation I don't understand, which is a solvable problem. But number two is that you needed to know the complexity of the neural network. So if you change your neural network, okay, and there is an inherent approximation of estimating the complexity of neural network. So I said, well, we need a better solution. So here's the key idea. I go back to what I was saying. The residual, even though they're not perfect, they're telling me something. Let's read that, okay? So this is the main idea here. So we're gonna use the residual loss, the residual loss as a key method to bound errors. Okay, so let's talk a little notation so we can do that. So first of all, this is my differential equation. Again, D is the differential operator. Now the pin solution I denote as UNN as I did before. So now D UNN is equal to F plus something, right? Because it's not exact, right? So, and this is the same thing. We assume we satisfy initial conditions, so I don't have to worry about it. And the goal here basically is to minimize this R, the mistake. Okay. Someone will have asked, but you have a different notation. So I kind of absorb the H into the differential equation, into the differential operator. I can do that, it's no problem. So now I have a simpler form, okay? Just notation-wise to be consistent, okay? All right, so I have that, and now with that, so the error is denoted as the difference between the neural network and the true solution, right? I don't know the true solution, but I write it like this. So the goal is to bound this eta as a scalar function of B such that the absolute value of n is smaller or equal to this function B, right? Okay. All right. So how do we do that? Let's do first, and in the paper we publish, we have linear ODE with constant coefficient, linear ODE with no constant coefficient, system of linear ODEs, non-linear ODEs, PDEs, system of PDEs. We haven't done non-linear PDEs yet. We have done, and it's not in the paper, we have finished stochastic differential equation. So we're just chunking along. So if you're wondering why I didn't do everything, it's a lot of work. So we're working along, chunking along, solving problems as we go. So, and we're looking for people, by the way. So, all right, so I start with the linear now. I'm gonna do linear ODE. So I change the D to L. So it's a linear operator is equal to FT. And I'm doing it in some temporal domain 0 to T. So now I have the T as we pointed out. So the operator on U is equal to that. And so I assume we satisfy the initial condition. And that L thing is a linear differential operator. Yeah, if I solve this problem, I'm happy. So now this turns out that if I operate on eta, which is the difference between U and UN, it turns out to be this equation. Okay, so the differential equation now change into the operator on the difference between the true and the neural network solution to be the difference between them. Okay, cool. and of course the initial conditions. Just to remind you, eta is the difference between my solution. All right, now we're gonna have fun. So I'm claiming there is an inverse to that linear operator, okay? So, and I said existing, uniqueness theorems, okay? So students can go read that. So now if I apply this inverse operator on both sides, so I have eta to be the inverse of that operation to that. Now you say, how do you invert a differential operator? And that's what we're gonna do now. So if we bound the absolute, if we bound this, the absolute value of t is equivalent as bounding that side, right? Okay, so the bound of my eta, which is what I'm looking for, will be the bound of the right-hand side, okay? Now, before I embark, I want to point out a few things. The first one is that this bound of eta only depends on the differential operator L and the residual information, okay? And that's what I was looking for. Don't worry about complexity of the neural network. Don't worry about anything. You see actually, let's put it this. The solution is not in there. It doesn't matter how I find the solution. It doesn't matter the parameters of the P. It doesn't matter on the forcing function, and it doesn't matter in the initial condition. Everything is encapsulated into this, right? So that means if I know they are, I calculate, I should be able to do that, assuming I can invert that operator, yes.
Yeah, I'm not sure I understand why knowing the R is something that we have, because we don't know U, right? So how do we know the residual any better if we don't know the ground truth solution?
The R is the residual. Hold on. Let's look at that. Okay, so if I put this on the left-hand side, that's a residual.
But, I
Yeah.
just had the same question, yeah, but when you've defined RT,
It's
it's not.
It's a residual
I'm so sorry,
idea.
I've confused eta and R.
so remember when I do these, and again, I don't know this. So let's say I have some solution like that, right? Yeah. I know the residual is the differential equation to the left with the forcing function to the left.
And you know the forcing function.
I do know the forcing. I said that from the beginning. Okay, so I know the residual.
Okay, so you're exchanging needing to know U or compute data for only needing to know the forcing function.
Yeah.
Which you have access to once you have that.
Now, this talk is I know the differential equation. Another talk if I don't know the differential.
All right, thank you.
I know the forcing function and I know the potential and I know the equation of motion. But with that in mind, this is for me was very important because I don't need to find the complexity of the neural network because it doesn't matter. I don't need to know what the solution is. It doesn't matter. Whatever the forcing function, it doesn't matter, and it doesn't matter in initial condition. As long as I can evaluate my residual and I can invert that L, I can find the error bound, which is all I was after. Okay, now the question is, how do we invert that thing? Okay, so here's my linear differential operator. I write it like that. I go from 0 to n minus 1, and I put the other inside. So I have one coefficient. I divide by that, so I have one less coefficient. Is that clear? Yeah. So the question is, how we inverting this thing? Okay, so if we can decompose this into a sequence of small, simple integral operators, and then I can invert each one of them, then I'm free, right? So how do we do that? We've done it. We all done it at some point in high school. Characteristic polynomials. Let me explain. And this is one of those moments. So if you have a polynomial, right, you can factorize with the characteristic polynomial where lambda j is the eigenvalues of the system, right? So that means I can take any one of these and I just decompose into the product. Well, if I can do that, I can do it from the L. So now instead of writing this form, I write it as characteristic polynomial. This is the most important slide of the talk. It took me 3 days to figure it. Okay, so once I have that, then let's say, can I invert any one of these? Doesn't matter. And then I'm just going to operate one after the other. All right, so these, I claim, and you can check it, if I do this, the inverse of this on the function R or any function for that matter is equal to that. How did I find that out? ChatGPT. No, in the textbook. Right? Huh? Go ahead. Yeah. Well, you can convince yourself by multiplying both sides by this, you get that, right? Yeah. So that means I can invert one of these little things, right? So, and I'm gonna call it this I, calligraphic I of lambda to be equal to that, right? So that's the inverse of this operator on R, it gives me that. Okay, now I think the rest you can see where I'm gonna go with that, right? All right, so I have that. So now I have a product of this, and each one of them I know how to invert. And therefore, the inverse of that operator is composition, it's not a product of those operators, right? So we give us eta to be the inverse of that is that. Now I'm ready to rock and roll. Okay. All right, so let's take that. And now there's one more thing important here. So remember that formula. So now I'm gonna make this statement that the absolute value of that operator, the inverse operator on R, would be smaller or equal to the absolute value of this function R times the real value of the lambda. Okay. And this, let's do the proof together. So I write the absolute value, I put the e to the lambda t, the integral with that. That I can just put the absolute values there. Okay. Now this, this one is e to the lambda t. I never said lambda is real, it's complex number. So I'm just taking the real value times this, which is going to be smaller than by putting the absolute value inside, right? Okay, I hope that convinced you, right? Now, with that, look at this. That means I do the magnitude of this is going to be the real value of lambda for this operator times that. And to do that, I use my formula before. If you look at this, it says I on lambda RT is e to the lambda. So because I have real, I substitute that with real and I get that. Okay. Now, so now I can apply this to one after the other, right? And now one thing I wanted to show is that this is an integral I can take care of.
But you still need to find lambda.
Lambda, the characteristic is the eigenvalues.
How do you get the eigenvalue for the difference?
It's a characteristic polynomial. It's a coefficients.
How do you get it?
That's the one I said it took me 3 days. Yeah.
More of a conceptual question. So, this approach doesn't depend on the level.
No.
Right? So you can also apply this to like numerical methods. And do you get the same error bound? Or I expect like those are bound. Those are like that.
Bloody good question. I don't know the answer, but you should. Yeah, I don't know the answer. It's a very good question. We apply this to R of the numerical methods. Yes. Fortunately, I haven't thought about it, but good. What's your name?
Yankee.
Kinky. You're my chair.
Yeah.
I feel this all like a play, you know, the plan is stuck.
I know where to find you. Yeah, good question. Yes, I kind of recognize you now. Sorry. All right. All right. So now I'm going to apply this one after the other, and I think the rest is kind of obvious because I'm going to take these, and then I'm just going to keep using triangular inequality. Just keep pumping these things out, right? And you can see that, right? So this is just this inequality, this triangular inequality. I just keep getting more and more. So that means that we have now the tight bound to be all these things times the absolute value of the residuals. Ta-da! Yes,
What's the dimension of T here, the one dimension?
for this is one dimension, so these, we have done it for PDs.
Okay.
And to do that, I have slides, so that one quick slide, how to do it. You get these characteristic lines, you solve it there, and then you transform.
And you said the residual actually know it.
Yes,
If you know it, you know the invert, you can do better than bound. Why don't you use it for correcting it, for correcting error? You can actually calculate it, right?
no, the residual is get as numericals, right? But that is, I can't just have it, it's like chicken and eggs, right?
I see. So when you say know it, you mean you know the function form.
No, I know
You
the
have
values. I know the values. I evaluate.
Okay, if you have a value of some enough keys.
Yeah.
Would you be able to approximate this and have some corrections as well?
No, but I don't know where is it on the U or is in the other thing? I can't take the R and add it to my U and say is the end of the day, right? Because the R is not the difference between, okay, let me explain. The R is not the difference between the true solution and the numerical solution. That's it. R is a residual of the differential equation. So I can't add the R to U. Does that make sense, or shall I write that?
But you have you have this R.
Right.
Is the difference between.
No.
the solution and the F, the true F.
Yes, not the solution. R is the residual of the differential equation,
Which-
not the U minus
Not the
U.
U.
If I knew eta, I could have done.
Sure,
it,
sure.
but yep. Okay. All right, so this is it. Is the what we call the tight bound. So we have to calculate these little integrals. We can do it trapezoid rules, and yeah, we're happy to do that. Are we done? Not even close. We call it B tight. That means there is B loose. And why do I care about B loose? Because I wanted to get a little bit better intuition on how things work. So the loose thing is just basically just to give you the high level thing. These integrals, where are they? Give me one of them. That's a problem with too many animations. Okay. So you see this integral I end up here. So I'm going to approximate that with the upper bound. It's just going to be a looser thing, but it will give me a little bit of a sense of scaling and how things behave. Right? So let's do that very quickly. And okay. So we're going to split into two. If the real value of L of lambda is 0, that means we only have oscillations. Then I have the I0 here, and I got this integral. Well, psi is the R in my case. So in this case, I'm going to get the maximum times the range, right? So I'm just boxing it. If the real value of lambda is 0, is not going out of control, I just make a little box and I just put it in there. Is that clear? This integral here is approximately with the maximum value of psi times the range, right?
That's very loose, but that's what you want.
It is loose and it's only good when lambda is equal to 0. If lambda is, and then now we apply this one after the other, you're gonna get some t to the m maximum of this and then the factorial, because the derivative is multiple, not a derivative, an integral of integral of integral of integral, so you get that, right? Loose. But now if lambda is, the real value of lambda is not 0, if the real value of lambda is bigger than 0, I'm not gonna bother because it seems that it's unbounded. If the real value of lambda is less than 0, then I can play a little game, and I'm not gonna get into the details, but in this case, we get the maximum, but we still have the real value here. And then after some math, we get 1 over the real value of lambda times the maximum, okay? So that's bounded, kind of loose, but now you can see a few things. Now my bound for eta, which I care, is gonna be ZT over V factorial Z is the number of eigenvalues I get that they have real zero. And this C here, where is my C here, is a product of all of them that they're not zero, but smaller than zero. And this gives me a good, this was important to me because I needed to think, what does it mean, this thing? Well, if the lambda is zero, it means you have a bunch of oscillations. More modes of oscillation you have, your error is going to get bigger, and it looks to follow the right thing. If your lambdas are, the real value is smaller than zero, it means you have decays, right? And bigger the lambda, faster the decay, better the error is going to be. So at least that works well. Okay, I see you're getting a little bit impatient. The next thing we did is nonlinear ODs, which now gets much more complicated. But we did one trick. The first trick we did, I mean, the most important trick here is that we expanded the U as a perturbation. So now it's a perturbation method. So we have these U0, U1, U2 are not at zero. Is the zero mode, the first mode as a perturbation method. And because the perturbation expansion, this epsilon should be, these things work for every value of epsilon, so you start matching terms. And then we end up is a series of linear equations. And it's iterative, meaning this one it has zero, the zero mode, the zero expansion term to the k, and then et cetera, et cetera. But this is solved from here. So iteratively, we can do that. And then you add the error bounds in some triangular inequality, and we end up with error bounds for that. And I'm not going to get into the details, but it works the same way. Yes.
Sorry, that
Yeah,
I'm
yeah.
still confused. Now I'm thinking about more. Your error bound is on the what do you call the what's the notation you use for the difference between
Eta,
right?
Yeah.
Your error bound is on the eta. By converting the operator, you have converted from the residual to the solution space. So why can't you do it? I'm still confused. That's what L inverse is doing. L inverse is say, take the, right, because if you can invert it, like what this is saying, because it seems like you actually have the bounds is, you can do the integration.
I follow you. I think I'm going to rephrase it in the following.
Okay.
You say, look, you inverted it. Once you invert it, integrate and put it back, right? So,
well, at least, but if you have a bound, if I can do a little bit better than the bound, I know there's a numeric error
Right.
introduced by integration,
Yeah.
but you can
Plus-
do some correction.
no, plus is now you have plus or minus and you have variations. So that means I have to integrate it for every space and add it all up. So yes, that would work, but we're back to integrating the differential equation by hand. I mean,
Okay, so that's a trade-off. So
Yeah.
you want to, but you don't have to integrate all the way down. For example, integrate the 1 or 2, 3 operator, the inverse ones, then you get better. And so you will, the bounce gets better, and if you have enough computation, it's kind of in between.
yes. Yeah, I
understand.
no, it's just maybe we can try this, or what the young said, we can try it on Numerica, but there is some thing where I could just invert a few times and see how it goes, and then do that, right? So we can start with the higher eigenvalues because that's the most important. And just go-
Like a
yeah,
principal
yeah.
component, a few.
I haven't,
Yeah.
we haven't tried that, but.
Well, there's no free lunch, but I want to conceptually understand.
Not only this on freelance, this is the work by me and one master student. So we just started it. Now we're gonna start doing more and more things. This actually, most of this was a weekend in New Hampshire. I didn't have a car. I was stuck home and I just played. Okay. I think. Okay. The other thing is when you do PD, it's a little more complicated. So what we do, we go into this called characteristic curves of the PD, and those becomes ODEs, and we solve it there, and then we propagate to the out. I said read the paper for that. So let's look at some results, and I'm almost done. So what we did here, we did something called manufacturer solution, which is my best friend these days. So manufacturer solution means I can just cook up any solution I want, anything you want. I'm changing the forcing function such as that function is a solution to the differential equation. Okay. But if I do that, I know the exact solution, and now I can calculate the exact error. So what you see here, this is the equation. We put some function, forcing function to give us some solution we wanted. The blue one is the exact value of the error bounds. This is my tight bounds, and this is my loose, very loose. But at least it's a bound, right? This is another equation. This is the true error. This is the tight, and the thing that doesn't have a loose because it has no zero thing. It's an exponential. Then we tried with a system of all these. Again, this is the true error. And this is my tight bound. Not bad, right? And this can get better with more integrations and more stuff. But this is another one. This is not linear. All these. This is Duffing equation, which is not easy. Again, this is the order. And you can, as I increase the number of terms on my perturbation, I go down. If I increase it more, it comes down. But you can see even for epsilon 0.9, which is very nonlinear, we bound it. Okay. All right. Maybe not convinced this is for PDs, but look at this. Look at this horse. I mean, the blue is the true error. The red is our bounds. Look at how tight we are. It's like the blanket on top, right? So that's a really tight bound. And when I saw these results, I said, no way. I look at this. And this is incredible tight bound we get to. Okay, so for this one, we integrate more and we did a little more work. Okay, so yes.
So if you sold this to us and said that we can measure this bound and then just keep training or make sure our network more complex until the bound is right. Is it fast enough to evaluate?
Yeah, it is actually. I have some algorithmic things.
And do you mostly change the number of X's that you're training on, or do you actually just modify the number?
No, the way we did it, we fixed the X's, and then
You just add nodes.
you after some epochs, we measure the residuals, we calculate that, and then we say it has to be below that, and then when we hit it, we stop.
And you just keep training the same network, or do you adaptively modify that?
No, the same network,
The
the
same
same network. Yeah.
Is it possible you'll never achieve that bound?
Yeah,
Given network structure?
like anything, right? You put the
Yeah.
tolerance, or it's just I had.
Okay.
Yeah, it's the same with any optimization, right?
Okay.
You put the tolerance, but sometimes you don't achieve it. You get the warning. You've seen the warning. Yes, it's the same thing. We don't have a warning, but it comes in. Yes.
Question from the chat, from Fabrizia.
Yeah.
Was, how do you know the order of
Fabrizia from
Fabrizia Guggenheim
from ISO.
from ISO?
Yeah, I met her 2 weeks ago. Hi, Fabrizia.
Actually, she can ask the question.
Yes.
How do you know the order of the equations? Or in other words, how many components characterize the piecewise function?
As I said earlier, in this work, we know the order of the equation. We know the differential equation. We know the equations of motion. And it's not an unreasonable thing to say, I know the equations of motion, right? I mean, we've done it with modified gravity. We have the Einstein field theory. We can apply it. There is some interesting stuff happening. I'll give you 2 examples. One is with the holographic principle. We don't know the scalar potential, and we're discovering it at the same time. We've done it. And then the other one we're working is with stochastic processes that you don't know what stochastic process you have, and you have it as an unknown. Again, it's another lecture. I can go through in details how you do that, but it works. But in all this I talked so far today is we assume we know the equation of motions, the differential. Okay, is it finally over? This is the advertisement. So it's an 8 lectures actually, starts on January 8 to 12, and then the break, and then 16 to 18. It's an hour and a half lecture, and then a lab, hands-on. We have quizzes, exercises, URL is here. Please sign up. It's a special early bird thing for Harvard, $75. If you're wondering, I'm not making money out of that, just for if that technology things work in Canvas and everything works. Jolly, most of these things do work. So yeah, it's gonna be a lot of fun. We cover from the beginning to how do we do transfer learning, how we parameterize, how we find the physics, this is gonna, in one of the lectures, a little more extended. We also cover a little bit about numerical methods so we can compare them. Yes, and how you sample, how you satisfy boundary conditions. I just said, oh, there's a trick to that. I have a whole lecture on how to do that. And with that, thank you very much.
I just want to mention to the students in this class, we will pay for that.
Oh, great.
Only if you register for this class, that's how I can take your for 7, 10.
All right. If you register for this class, you get that for free.
Yeah.
Oh, I like that.
Jeff has a.
Yeah.
Jeff Scarborough, go ahead. Go ahead, Jeff.
Oh, thanks for this really nice talk. I enjoyed it. But I have a question about what I think is a slightly different problem. It's more like propagation of errors rather than upper error bounds. But for example, suppose you think of the forcing function as something that has uncertainty in it, that you want to consider maybe a standard forcing function and a perturbation, or two completely different ones. I'm a little confused as to whether you had a slide saying the forcing function doesn't matter, but does your analysis include that kind of propagation of uncertainty in the forcing function, and the initial conditions too, I guess, would be the same?
No, Jeff, good question. For all these things we have done, this formulation, we didn't put anything else but what I call epistemic error of the model. Once you have this, you now can do, for example, we're doing MCMC, where we add the other errors in the likelihood or priors and the whole thing. It's just now you have an extra error that comes from the epistemic error. So all these things that the error on the forcing function, error on the thing, the way I will treat it, and I haven't done it, is to treat it as extra error that it will come into the likelihood, I assume, right? So, yeah, I mean, this is what is this class all about, right? Doing the rest. So,
Yes, okay. Thanks, Pavlos. Really nice talk. I appreciate it.
thank you, Jeff. Yeah.
Sorry, you go ahead. You go ahead.
Yeah, this one slide mentioning that we realized that the error bound does not depend on the parameter.
Yes.
But it certainly depends on the parameterization of the network, right? So the
does.
architecture.
Well, let me explain. It does depend, but I capture everything from the residual. So instead of going and say, oh, and there's, as I said, there's quite extensive literature saying the complexity of the model is number of nodes times parameters to some power of whatever, right? Instead of doing that, I'm just saying all the complexity of the neural network is captured by the residual. So I don't have
Like
to
all
worry.
the information that you need to derive the bounds.
Yes, it's in the residual.
Yeah.
Yeah. And that was the key idea when I started this work. I wanted to not to have to go into the neural network, worry about what's the activation function, blah, blah, blah. I said, I have the residual tells me everything I need to know. And from there, can I get the bounds?
But instead, I mean, like, if you find, for example, that the error bound is still too large, you could just say, okay, maybe need a different architecture.
Yeah.
Okay, that makes sense.
But it's more heuristic at that level. So I don't have it in the thing. So I cannot say, oh, let's parameterize the error bound with the parameters and do that. So the way I presented it, trying to make it as formal as possible, is fix the network, do the work. And if it doesn't get to where you are, change the network and do the work. Yes, John.
So I want to ask you more kind of a conceptual question, especially because late in the beginning. Sorry about that, and still want to hear. Am I correct that what you're doing here is thinking like a human, when a human looks at differential equation, we use all the tools we have learned doing, integration, trying to invert in some mathematical way.
Yeah.
Now you're saying you're basically thinking about like AI. You say, okay, there is this tool, right? This tool essentially was originally designed to approximate any function. But now you say the function is defined by this differential equation, you have information on its derivative, right?
Yeah.
So am I correct that one way to think about it is really you are developing, in a way, it's an AI tool to replace humans' ability to integrate things, but it's not numerical integration.
No.
Right, it's a bit different from your integration. What I want to push is the following. The two things. One is there's lots of differential equations we humans don't know how to solve, right?
No, I just parenthetically, I say, and I know a lot of my friends,
Yeah.
the biggest failure of mathematics is solving differential equations.
Right.
Most of them actually don't have it.
So exactly. So this is another way to do something.
Right.
Number one. Number two, sometimes we write out differential equations and we don't even know whether the solution exists to those unique source of force.
Yeah.
The question is it possible here by doing training, it can help you to determine whether one has a solution or not unique or whatever it is. Is it possible to do that?
Well, I'm not sure exactly that, but the thing we're working on now is we solve the equation.
Yeah.
And then I say, well, now I have a black box, right?
Right.
So the field is a black box, a neural network, which makes some people uncomfortable, right? So, and I said, well, can I come with a form of the solution the neural network found, right?
Sure.
So we start using symbolic regression,
Okay.
and now we're coming out with the functional form approximation to the approximation, which is a neural network. It's kind of lovely in some ways because for a particular problem, the physicists have an idea or some convergence, at the very large scale or they knew how it would go. So then we did it, so now we have a neural network. I did a symbolic regression and we confirmed the divergence that they had in mind.
I see.
And I think, symbolic regression, I don't know if you're familiar with it. It has its own questions. I'm not totally sold on it, but it can be used as an interpretation method of what we find.
It's like it's building an emulator.
It's kind of more of an interpreter. So I have a black box now. What does this black box mean? How does it behave in large fields? How does it behave? Does it have any poles? Does it have anything? So by doing the symbolic regression, it helps us interpret those black boxes. I don't know exactly if that answers some of the question.
Thank you.
Yeah. You're skeptical of symbolic regression too? Yeah. I was very
Can I ask a
fascinated until I started reading the papers.
Can I override you for a moment? Because Fabrizia asked, so you differentiate systematic from random system, right?
Say again?
Not entirely sure I understand the question.
Can
Fabrizia.
you read again?
So
Yeah, when you were discussing before about the possibility, so from the question of Jeff, the possibility of taking into account also extra uncertainties, right? Uncertainty that come from the other process and then propagated to the final solution. You differentiate, you would add this systematic error into your final solution.
I wouldn't, I don't know how, actually, to be honest with you, I shouldn't sound like I know what I'm talking about, but what I will do is do proper statistical treatment at that point. So
Okay.
the U has an error, which we have, actually even this is an upper bound. There's another work we've done that we use the error bounds to calibrate the uncertainty quantification of the neural network. Use that, and then you do just proper, what I call proper statistical treatment. Everything has the stochasticity and just do MCMC and just find.
Okay.
That's what I will do, but maybe there's another.
Thank you.
One general question about the way that you formulated these networks. Do they transfer when you change the boundary conditions very easily? Like you built the boundary condition in the training, but most of the network should know the dynamics and not encode the.
Yeah. This is lecture 4 and 5 in the course. It's called.
Okay. Can you tell me the answer?
Yes, the answer is 2 ways
You
of.
have to pay though.
I'll give you half of them.
Okay.
So,
Get that.
there is two ways of doing it. The first one is, I don't know if you can see. So X, U, right? So the initial condition, let's call it theta. I can put it as an input. And I can train the network for a bunch of X and bunch of initial conditions. So we call that the bundle solution. That means now I train one network for all kind of initial conditions. That's the first way of doing it. The other way of doing it is I still have U. This may confuse you a little bit, but if I have more time, we can go. So instead of solving the differential equation directly, what I'm gonna do, I'm gonna try to discover the manifold of all the solutions, okay, which I'm gonna call H. And H is a high dimensional space. So it's the same idea that we've seen many times, that if you project something in the high dimensional space, it's easier than to project it down to the solution. So I take this is a high dimensional space.
So U has to live in H, but H doesn't, like,
No,
every
no.
element of H does not have to be a U.
The U will be a linear combination of H's.
But not all linear combination of H's need to be a good solution. Right, this is a
Yes.
set of
Yeah. So now I can solve it for multiple U-naught initial conditions. And then that means the H is a good manifold for all of them, and then I just project down. Now, if it's a linear equation, then I can project with one shot because it's a quadratic. So I can minimize. No gradient descent, no nothing, just boom. If it's not linear and it has polynomial degrees, I can use the same idea as perturbation and I just project it. If it's some strange nonlinear form, we haven't done it. But we'll think it differently. There's some ideas in, does anybody know Lie algebra here?
We heard the term.
Yeah. So there is some ideas in Lie algebra. We're looking that manifold can be projected directly with linear value, and then you can invert it again. Kind of similar what I did. Okay, question.
Can I follow up on the first solution?
Of
and
course.
ask, now do error bound quantification, you sample over theta, and then you make a claim for most reasonable theta as a function of T?
Okay, again, I haven't done that, but without PDEs. And PDEs are the same, so it should map to that.
All right, so we are actually,
One more question.
Yeah.
You mentioned about what you're doing here so far, there's no data, right? So kind of a deterministic.
Yeah.
I wonder that even for the deterministic terms, maybe it might be worthwhile to introduce some errors, because you mentioned this issue of, for example, it could be very sensitive, right? You could have deviated a small portion,
Yeah.
then it shoots very far, right? But if you have random error in the system, the neural network should learn not to be very sensitive to small particles,
Yeah.
because they need to resist to that. So maybe there is a benefit actually for solving deterministic ones. You introduce this thing, because that will teach it not to do those very dramatic, because this is the chaotic system.
Yeah.
It's different, right?
I think you're right. I think when we have data, we would. I mean, we have data and that will actually help us in some ways, right? I'm not sure how to bound it, the epistemic error though.
But then you will be bounding stochastic. I mean, it will
Yeah.
be stochastic bound, not a deterministic bound.
Yeah, but the bound only comes from due to the error in the data, not the misspecification error, right? Or just I put it there, catch it all, like I do in the 109.
Right.
Okay,
Typically the misspecification, the errors, the question, we don't
yeah, we
distinguish them.
just put it in there.
Whatever it's that, it's the ridiculous, that's
Yeah.
what it means, right?
Well, that's what I do in CS 109, but we can do that. Just put it everything there, catch it all and treat it in the flow. Yeah.
all right, let's thank Pavlos.
Yeah, thank you guys. Don't forget to sign up.
Yeah.
Thank you very much.
Nothing. Actually, they pay me nothing, but more people I have,